and also inviting me to the very interesting, what I should say is workshop, which is the start of the conference for the next month. And I think it started off on the right note, which is first speaker could barely get started before everyone started asking him, before everyone asked him questions. And I like that spirit, and let's try to keep it up. I have the laser. This is a theoretical talk, and I'm going to give 2 theorems. I'm not going to apologize for the theorems. I am going to try to explain them. I might not give complete proofs. I'll try to say why they might be interesting. So let's see, who do I work with? Oh, outline first. I'm going to tell you about 2 ODEs. Their motivation. We could solve them in our head, but their motivation. Then I'm going to talk about surface water waves as a Hamiltonian system, for which I'm very grateful to Peter, who's, I guess, not here, but he gave an introduction which had Hamiltonians, which Zakharov's Hamiltonian, and he talked about canonical variables. They'll be important to us. So I'm going to do it again, maybe slightly more leisurely, with maybe some more information about that. Everyone knows that when you have a Hamiltonian system, it's standard to look for a normal form. So I'm going to tell you about this PDE, which is also a Hamiltonian system. I'm going to talk about its normal form. And I'm not going to do that just on a formal calculational level. I want to prove a theorem about the normal form and about the mapping properties of the transformation to normal form. So that's going to be the key. I have to explain what the implications of the normal form are, and I also have to explain why I want to do that. Then I'll give you a proof of the theorem of the normal forms, but I promise that's going to be 2 slides max. And then to make it a full circle, I'm going to give a critique. Very nice waves coming through the window. I'm going to give a critique of the normal form. Partly having to do with what is left to do, because this is really a work in progress. This is a step in maybe some bigger projects, and that all of this is joint work with Kathleen Sulem, who's at the University of Toronto, which is close to where I am. So I acknowledge support from several sources. So let's go. We can solve this equation. Maybe z is a complex number, and we can solve the ODE z dot is equal to z squared. And I'm going to give initial data z of 0 equals epsilon. And then the solution is exactly epsilon upon 1 minus epsilon t, and that tells you that a singularity forms at time equals 1 upon epsilon. Z could be real or could be complex. But if we have a slightly different equation, w dot is equal to w cubed, where w0 is equal to epsilon, then there's a slightly different solution, square root of an expression, where the denominator now vanishes at when t is equal to 1 over 2 epsilon squared, which is an extended lifetime from the 1 upon epsilon. And so if I solve term equations with quadratic nonlinearities, I can't guarantee their existence for longer than 1 upon epsilon, but if they only have cubic nonlinearities, the lesson is I have an extended lifetime. And these are awfully simple, but the basic time of existence, that is, if you ask uniformity over a ball of radius epsilon or something, you can't change that by, say, adding a linear term, the I omega z, or the I omega w, or higher order perturbations. So by h3, I mean something that's a cubic or higher, and k4, I mean something that's quadratic or higher. Okay, lesson. Quartic or higher. Quartic or higher. Lesson taken into account. Let's go to water waves. Peter gave a nice lecture on the equations for water waves. I don't have to say very much after that, except I would like my fluid domain to be x in either 2 or 3 dimensions. That's, sorry, x is in 1 or 2 dimensions. That's the surface. I'm going to parameterize coordinatize my vertical axis by y. Gives me uniform notation. And my usual joke is, this is pre-Columbian water waves. because the Earth is infinite and flat. And if we work on a sphere, well, it's slightly different on small local coordinates. Incompressibility and irrotationality are standard for us. We don't allow rotation. Some people do. I'm going to stay with the simplest case. That says I have a velocity potential function, and it satisfies Neumann. It's harmonic and satisfies Neumann boundary conditions on solid surfaces, such as on the bottom. And it gives us Euler's equation, which are I don't think anyone has an argument with it, and I think everyone in this room is quite familiar with it, the kinematic condition and the Bernoulli, kinematic equation and the Bernoulli condition. No questions so far.
One question, eta is a function of time also, right? Up there, why?
Fluid domain. You have to adapt the phase space point of view, which is a solution is a curve in a space of configurations. And a particular configuration is a function of x, but a solution will be a curve, therefore a function of time among the functions of x. So eta indeed is a function of x and t, but a configuration is given by an eta of x. And now I want to move among the configurations. It's a phase space point of view. C also, phase space point of view. Thank you. Good question. Just to give you an example of what you can do solving these equations is a calculation that Philippe Guillen did very nicely a few years ago, a growing number of years ago, in a paper that I published with several co-authors. And time goes from back to front, and here's a clean interaction of two solitary waves. These should be as asymptotic at minus t goes to minus infinity, nice pure solitary waves, and this exhibits a little bit of a ripple behind them as they interact, but has relatively little to do with the rest of the talk. Zakharov wrote a Hamiltonian for this system, and I just want to spend a few moments reviewing this. There's an energy functional. Energy functional we call H because it's going to be the Hamiltonian. It's made out of a kinetic energy term and a potential energy term. And it's very easy to guess what the energy is and to write it down because it's a physical system. The kinetic energy should be half velocity squared, sum over all the fluid particles. And the potential energy should be g times the elevation, sum over all the particles. Well, you and I can integrate the function y over this domain, and we get eta squared, g over 2 eta squared, minus a constant. And u is given by the gradient of a potential function. So that's essentially, that's the Dirichlet integral over the fluid domain. Let's throw the constant out, despite the fact, if anybody calculated it, it's infinity. Let's rewrite the kinetic energy, well, by integration by parts. So I have half grad phi squared, double integral over the fluid region, or multiple integral, d-fold integral over the fluid region. I integrate by parts. I'm going to get half phi Laplacian phi plus boundary terms. First boundary term is on the bottom, involving the normal derivative of the gradient of phi, and the second boundary term is over the top, involving normal derivative of phi at the free surface.
Is the lower limit minus h?
Talking about the c? We're talking about here.
Integral h to eta.
It's a minus h to eta. Yes, thank you. Otherwise, it's a little funny. And if I define at this point the boundary values of the velocity potential to be, well, it's a little confusing in Zakharov's paper. He calls it a capital phi, but that's a little too close to little phi, so I'm going to call it I have been calling it a completely different variable, c. Then I can rewrite the kinetic energy in terms of c. Where do I see that? There's a c. This is a complicated operator on c. And this, the surface element with regard to the free surface is a function of eta. But I can rewrite the whole thing in terms of the Dirichlet-Neumann operator, complicated and non-local function of eta if I use xi. This xi is that xi, and g eta xi is the normal derivative. You all know this. I should be moving faster. Writing this, the Hamiltonian becomes quite simple, and in particular quadratic in xi, and a little complicated in eta. And to be a little bit more precise about the Dirichlet-Neumann operator, That's that operator that took the normal derivative on the free surface times the normalizing function and gave me this combination of which is rewritten here. It gives me the operator G eta xc. That's linear in xc. It's nonlinear and non-local in eta, and it pays to know a certain amount about it. And the theorem of Zakharov, well, we just calculated energy. It's extremely simple. But the theorem of Zakharov is that eta and xc are canonical conjugate variables for the water wave problem with this Hamiltonian. And it's, in fact, this Hamiltonian in Darboux coordinates. So, in my mind, it's completely easy to know the energy because the energy is the physical energy, the physical expression of the energy from the problem at hand. What was mysterious is how did he know that these are the variables in which you have to know the variables, maybe even before you know the Hamiltonian. And so that was just, I thought, out of Zakharov's head. But I learned later there's actually a derivation from first principles. If you agree that the first principles of mechanics are the first principles. And so it takes me one short page to do that, so I thought I'd show that to you. So the Lagrangian, I gave you the Hamiltonian, but the Lagrangian for surface water waves is the difference between the kinetic and potential energies. That's the way nature moves. So L is K minus P, but you're supposed to express it in terms of curves on configuration space. That is eta and eta dot, eta and d by dt of eta. So how do I write eta dot in terms of other variables? Or how do I write the kinetic energy in particular in terms of eta dot? Well, we have the kinematic condition that says eta dot is this expression, that's kinematic condition. I recognize that because I normalized it correctly as the Dirichlet-Neumann operator. So invert G on eta dot, and every time you see xc, use that. Gives you this expression for the Lagrangian, bunch of eta dots, an inverse, and a minus. And then what does mechanics tell you to do? It says the canonical variables are eta and L sub eta dot. Eta and L sub eta dot. Well, L sub eta dot is pretty easy to take. It's as a quadratic form, and it's self-adjoint, and so it just gives me G inverse eta. So it gives me eta, G inverse eta on eta dot, but that's xc. And so there's a derivation that he chose the right variables. Okay, that settles one mystery. Darboux coordinates tell me those equations of motion can now be written as eta dot is equal to gradient with respect to c of h. It's a quadratic form, even the half is ready, so it's the Dirichlet-Neumann operator on xc. And xc dot is equal to minus the gradient with respect to eta of h, which is, well, eta squared is easy to differentiate. It gives me eta. 2 eta cancels the half. And this is subtle, the gradient of the kinetic energy with respect to eta, and that involves the variational formula of Adamar, which, if you look back and think about, you can find it in his Collège de France lectures in 1910. It's an interesting fact that you take domain derivatives. And that's the last I'll say about that little thing, except I'd like to tell you a little bit about G itself. I need eta to have a little bit of smoothness, so I have a domain for my Laplace's equation, which has a little bit of boundary regularity, so I can actually know that the solution is smooth and unique and what have you. So let's make eta is equal to C1. Some people say, at least in 2 dimensions, Lipschitz is enough. Then G eta satisfies the following simple things. It's positive semi-definite. It could send something to 0. Actually, it sends one function to 0. That's 1. That's the constants. So G eta of 1 is equal to 0. That's the only one. It's self-adjoint if you chose the domain appropriately. It takes a derivative. So if I look in Sobolev space, it maps one derivative functions who have one square integrable derivative to functions which have no square integrable derivative, but themselves are square integrable. And a little bit more technical, as an operator, taking this set of functions to this set of functions turns out to be analytic in eta. And now there are various ways to say what a function is, which is analytic with respect to another function. But the easiest thing to say is it has Taylor expansion. I'll say that in one slide. Let's just go through there are, what is it, 9 conservation laws in 2 dimensions and 13 and 3. I want to give you 3 of them. the three obvious ones. So there's mass is conserved. Better be conserved. This is water. So let's prove it, but in the language of Hamiltonian systems. So to show that something's conserved, a quantity is conserved, you want its Poisson bracket to be 0 with regards to the Hamiltonian. So let's calculate that. Poisson bracket of m with h is the eta derivative of m with the xi derivative of h minus the xi derivative of m with eta derivative of h. And then you take the inner product, integral dx. And so let's see. M does not depend on xi, so that's out. And then the eta derivative of a function, which is integral of eta, is 1. So that's easy. And the grad xi with respect to h, we've already seen that on the right-hand side of the kinetic equation, so that's g eta xi. And g is self-adjoint, so you can put it on the 1, and that's the function which it kills. So that result is 0. You can do the same thing with momentum, and energy is obvious because that Poisson bracket is skew symmetric, so there are 3 conservation laws in that language of Hamiltonian systems. I told you that being analytic tells you have a reasonable Taylor expansion. That is, I'm not saying numerically it becomes more sensitive, but theoretically, if you give me a function which has sufficiently many square integrable derivatives, like 1, I can apply these Taylor polynomials to xi, and the result converges in L2. And to make that a little bit less obscure, let me do the following thing. I'm going to say capital D sub x is a partial by partial x divided by I. That makes it normalized nicely. And then I just have expressions for the first 3 Taylor polynomials, just to show you that both you and I can do it. It's really not so hard. Although after this they get a little bit long. What do I do with G and its Taylor expansion? Plug it in the Hamiltonian. Now I have a Hamiltonian with a Taylor expansion, and that reminds me of many situations in mechanics, say celestial mechanics, where you're at a stationary point. For us it's 0. And you would like to know the behavior of the Hamiltonian system near that point. So you're going to look at the truncated Hamiltonian and study the solution at that truncated Hamiltonian, and then maybe do perturbation theory to study solutions or special solutions or whatever. So I want to be in exactly the same situation as we are here. So when you do look at the Taylor series, or the truncated Taylor series, it's very traditional. I mean, it's a standard thing to do, is to try to eliminate unnecessary nonlinear terms. So if you can make a transformation which eliminates terms, it's good. Suppose you can eliminate all terms except the linear term in the equation. It's even better. You can solve it explicitly. So you want to simplify as much as possible. So for this, I'm going to, because I want to do analysis, I'm going to insist upon the following thing. Let's stick the dimension equals 2. That's the surface is 1 dimension. It's the lateral, solutions are constant in the lateral x2 direction, so to speak. And I also, because it will change the question, I would like to make x periodic with periods, say 2 pi. Anything you wish, but 2 pi. Then, and I'd like to take infinite depth, even more of a simplification. Then the frequencies are discrete, and they're given by root gk, for k integers. What's a normal form? I want a transformation, which I will call tau, to take a variable z, and then give, which is going to be my a tick c pair, and a new variable w, but maybe not everywhere, but at least in the neighborhood of the origin. And I want it to do a couple of things, a couple of constraints on that. I would like to keep the Hamiltonian system, because if I don't, the problem gets complicated and it's hard to iterate. So I'd like to stay within the category of Hamiltonian systems, so I'd like the transformation to be canonical. And Peter Jensen already expressed that it's important to stay among canonical transformations for a variety of reasons. Here's one. And the second thing I want to do is I want to design this transformation, tau, to eliminate unnecessary terms and keep only absolute minimal nonlinear terms that are expressions of the interaction of the problem. And an nth order Birkhoff normal forms transformation will normalize up to nth order in the Hamiltonian, and then we'll leave some Taylor remainder. And generally, just to let you know, this is a process which doesn't converge as m goes to infinity, even in very low dimensional Hamiltonian systems. But nonetheless, yes?
If you were able to remove all the terms, let's imagine that you're able to. Does it mean that the system is integrable? Can you connect this with integrability in the sense
You can, it depends on the z's. Because the z's can give you non-integrable systems. Resonant terms are not necessarily integrable. You'll see it in a few slides. But generic resonant terms are integrable. So for non-generic reasons, and this one has it, there can be non-integrable terms. But you'll see it in a slide or two. It's a very good question. So the new Hamiltonian is going to be this up to mth order, and then you might say I'm going to approximate by truncation, look at my solutions, and maybe if I can prove that I can add them under perturbation theory, it might work. And the z's are only contain resonant terms. They contain no non-resonant terms. So it's part of Birkhoff normal forms transformation, and it's really an averaging, because the z's are ones which are invariant under averaging, and everything that vanishes under averaging. So it's really one method of performing averaging theory. And of course, I have not put in surface tension. I will mention surface tension later, so it's been prepared for me by Achilles, but have not put in surface tension. And so it's well known that there are no three-wave interactions, at least if you eliminate 0 as a valid wave number. So you can't sum 3 frequencies and 3 wave numbers and both get 0 if you have 3 non-zero wave numbers. And that means the third order coefficient, the third order Birkhoff normal form is 0. And that means the equation that you derive after making transformation is now starts at cubic order, because it's the derivative of the fourth order term in the Hamiltonian, and hence my W equation on my first slide rather than my Z equation on my first slide. So what's important to me, and why I'm giving theorems today about this, is I'd like to know the mapping properties. So you can make this by a formal analysis, a formal calculation, and then even you can go higher. But what I need to know is the mapping properties of that normal forms transformation, because I would like to have dynamical consequences. I want to know I start in which set of functions and I arrive after transformation in which set of functions. I need to know that that's bounded in some way. So, good question. Why should one be interested? So you're supposed to be a tough audience because you have a variety of backgrounds and everything, so I have to really work hard to show that you're interested. So the first one I set up for you, because I gave you those 2 ODEs, one with a longer existence time, guaranteed existence time, than the other. So I'd like to say something about existence time for the problem of water waves when when functions are periodic in X. If I had cubic terms present and I just do use standard arguments in an existence proof, it doesn't give me time of existence more than 1 upon epsilon, which is not really so much better than Cauchy-Kovalevsky. Yes, please.
What's the epsilon in this context?
Simply amplitude. Simply amplitude. Could be other things, but simply amplitude. If I eliminate quartic terms and I have a good existence theorem, then I at least get 1 upon epsilon squared. And that's good because that gives me NLS time scale rather than just simple shallow water time scale. So that's important to me, at least for the theory of maybe limits of shallow water or NLS. Well, here's another thing which is a compelling reason for me. Zakharov's theory of turbulence, which was also mentioned by Peter Janssen. It uses a reduction to normal forms. He called these original variables capital A and the target variables little a, but in Zakharov he says little a and little b. And his theory of his wave turbulence theory is for variables little b, And there's a transformation, tau, which goes here, which takes A into B. And A is made out of eta and xi and some Fourier multiplier operators. And B is where the theory of turbulence sits. And you'd like to know if you have any goals at making a rigorous, at making even pieces of that theory rigorous, you have to know how that mapping works. And so this would be required there. Yes, Ben?
On your first slide, wasn't the quadratic terms the ones that gave you 1 over epsilon time of existence?
Yeah.
So how come the cubic terms are the ones that are
Because
decided now?
the derivative of H3 is the equation.
Okay.
It's a Hamiltonian system. Yeah, counts are always off by 1. And I'm working in 2 or 3 dimensions, which is counter to some people work in 1 or 2 dimensions because you count the surface dimension rather than the fluid dimension. So numbers are hopeless. You have to just constantly be working to communicate about that. So there's a second reason. Here's a third reason. Special solutions, resonant terms, Z3 through Zm describe an average system, and that often has particular solutions of interest. For example, when we go to surface tension, there are 3 wave resonances which give rise to Wilton ripples. And what I didn't manage to fix on this slide is that KAM theory has a non-degeneracy condition, which is known as the Arnold condition sometimes, or known as a twist condition other times, but it's a nonlinear non-degeneracy condition, and it's very typical to have that condition expressed in terms of, well, proved by showing that it's true for the Birkhoff normal form. So if there's any idea, Pavel is going to talk to us about periodic solutions in a KAM type format in this talk following this. But if there's any hope for a generalization to, say, quasi-periodic motion, we have to know a certain non-degeneracy condition. Peter, you missed all the citations to your work.
That's right.
Okay, so let me give you a theorem. I have 2 theorems, one without surface tension and the other with surface tension. So I have to qualify this kind of carefully to get it right. Dimension is 2, that is, the surface dimension is 1 and vertical is 1. H, the depth is infinite. The bottom is not finite, it's infinite. I'm going to take a Sobolev index R, and it has to be bigger than a half, strictly bigger than. Then there exists a capital R0, that's a distance in Hilbert space, such that for any neighborhood R less than R0, in the following Hilbert space, HR plus 1, that's for the etas, HR, that's for the x's, the Birkhoff normal forms transformation is defined, and it maps this space to this space itself. That's what you need to have dynamical relevance. If you lose derivatives in your mapping, you've completely lost track of the error term, that truncation term, the T, that you have to eliminate by studying the normal form. So the result is that W is equal to tau 3 of Z, the transformation of the 2 third-order Birkhoff normal form gives you officially, on this space, a Hamiltonian H tilde, which has 0 here. And you only have 4th-order terms of the Hamiltonian, so 3rd-order terms in the equation. Okay, so that's nice. This was a while ago, but we also studied the surface tension case, but never wrote things down. So now we're desperately writing things down. Let's make positive surface tension. I'm going to refer to Achilles' talk to tell you how the surface tension fits into the Hamiltonian. I'm not sure he put down the Hamiltonian, so I can explain it to you later. I didn't put it on my slides. I could take any depth, positive surface tension, and take any R, but I need it greater than 1. Then it could be that Z3 is non-zero because there can be 3-wave resonances. In fact, there could be multiple 3-wave resonances. But they all sit in a compact set of K space. They can't be for large K, they're for a fixed set of Ks. The Ks can be quite large if surface tension is small, and that's usually the case. But in any case, it's bounded. They do not go to infinity, and that's important to mathematical analysis. In any case, this tau 3 is a symplectic transformation. It always has been a symplectic transformation. transformation for me. I need that. But in this case, it's an analytic diffeomorphism, meaning it says its own Taylor expansion, which means to say here, it isn't. It's it's a continuous mapping. It's only a smooth mapping if you consider it on a scale of spaces. That's another story, which I'm going to leave out of the talk. And here's a funny thing. Well, one of the beautiful ideas of Hamilton is that you should confuse what's in phase space. You should make a confusion over what is configuration space variables, that is what is a q, a position, and what is a momentum variable, that is p. For example, a canonical transformation takes q to p and p to minus q. That means you mix them up. Well, in this process, not only are we mixing up eta and xi, but they stand for different things. Eta gives me a domain, and xi gives me a field on the domain, and now I'm mixing them together. Kind of an interesting fact. Okay, nonetheless. How about fourth order Birkhoff normal forms? Well, I don't know anything at this point about surface tension, but I do know something at infinite depth. It has to do with a series of papers, but now it's 10 years ago, 20 years ago, oh my God, on fourth order resonances. So what can happen to fourth order? I need 4 frequencies, which sum or difference to 0. I need wave numbers to add to 0. And when can you have solutions of this? Well, they come in 2 families. It can be shown for deep water. One is if the omega 1 and 2 are the same, and omega 3 and 4 are the same, then of course you always get 0. And then you can get the momentum to work out by K1 is minus K2 and K3 is minus K4. Those are the generic resonances of the problem. But there are also a 2-parameter family of Benjamin Fehr resonances, where K is given by these sequence of squares, and omega is given by a square root of those of that sequence, with appropriately chosen sign. And those are all. And then there's, I heard a talk by Zakharov in Berkeley in '94 saying these coefficients vanish. And I thought that was kind of an amazing fact. Actually, I didn't believe him. So I went and calculated them myself, and yes, they do. These vanish, these are non-zero, and that turns out to be a fact. It's an basically an algebraic fact, although it does sit in infinite dimensions.
Wait, why do you write Benjamin Fehr resonant terms? Because in 1D propagation, so it's
Yeah.
2D problem, the Benjamin Fehr is never resonant in the sense that you never have that the 2 equations are satisfied exactly. Benjamin Fehr in 1D is a quasi-resonant process.
Well, this is an analog for Benjamin Fehr, because if I just put set m is equal to 1, then it's going to, then I have 1 and a pair and then another one, and so you can think of the first 3 as something in a sideband, and it goes to the other one. So it's a poetry. It's not really I don't think Benjamin nor Fehr associated this with that, and it's the periodic case, the space periodic case.
Yeah.
So okay, it's a little bit of poetry, if you forgive me. I'll take it. I'll erase it if you really insist.
No. It's just it was a question.
I'm not standing on enormous things like that. But anyway, Benjamin's dead. I think Fehr is still alive. I don't know. Yes.
The first case, is this
Yes.
for 1D or 2D?
This is for any D.
For any D.
For any D, because those are generic. Give me any Hamiltonian system, and it's going to have you can have self-resonance and another self-resonance, and those make a quartet. It's in some sense a little trivial.
Tell him he wasn't here when you were explaining how you mean D's.
Oh yes, what is my dimension? I like to think big. So if I have a 2-dimensional C, that's a 3-dimensional problem, because I have to solve underneath too, right?
Yeah, sure.
And if I have a 2-dimensional C, but it's all constant in the x2 direction and only varying in the x1 direction, then it's a 2-dimensional problem.
Oh.
And a 1-dimensional problem, I'm not sure what that even means, because that point on top. So capillary tube or something. Okay, that's just my convention. Okay, so let's just look at that 4th order normal form just for a second to do a bit of formal things. You can define action variables involving the Fourier coefficients of the solution. And I'm going to do, for each k, I'm going to do an I1 and an I2. Those are two action variables. And then I can write the Hamiltonian up to fourth order in terms of things which are linear in I and only depends on I1, and things which are quadratic in I, which only depend on I1 and I2. And there they are. And there's no angles. So it's integrable up to fourth order. Just to remind you, if I did, where were they? Let's see. If I did have these terms associated with these terms, it would not necessarily be integral. It would have complicated things. It turns out that this is integrable, and so it allows us to even extend our existence time conjecture, because I can solve, the quadratic part of the Hamiltonian. It's a linear equation. We can always solve that. The cubic Hamiltonian, that is the quadratic part of the equation, is 0. And now the quartic part of the Hamiltonian, which is the cubic part of the equation, is completely solvable. So the perturbation goes on top, but the perturbation you can control up to this amount of time. And I like that because it says I can, if I manage to prove this conjecture, I like that because it allows me to look at NLS situation. So in a modulation theory, modulational time scale, I can have true modulational interaction well past the time where there should be significant interaction, because I'll have even 1 upon epsilon number of interactions before my approximation breaks down and I have to worry about other things. But so far this is formal, and the Sobolev mapping properties of the tau sub 4, well, it's under investigation, but it's not so trivial. So I haven't got that quite yet. But anyway, that's something that we want to think about. So I'm talking fast. I'm allowed to finish at 20 of, quarter of.
What time did we start?
20 of,
That's right,
quarter
you-
of.
You have till quarter of, but any
I'm
time.
going to finish early because you haven't asked any questions.
Okay, I'll ask a question.
Now?
Okay, I can wait.
Any-
It's kind of an end question. I'll do it now. The assumption of spatial periodicity, is that relaxable or?
It's a very good question. Also, it depends. That also affects how long solutions last. So, and it affects the question quite a bit. So there are 2 settings in which analysis has been done. Most of it has been done on solutions on the whole R2 or the solutions on all of R. And if you start with localized solutions, what happens is they decay in L infinity. They decay in amplitude because they spread out. So if you can get them to spread out sufficiently if you can have a solution which lasts for a certain period of time until it's small in amplitude, then you can have it last to infinity. So that's or at least for very, very long times. And that's because it's under wave spreading. Some people say dispersion, but it's really just under wave spreading, amplitude decays. And that's a different setting than the periodic case. So it's actually harder to make something last a long time in the periodic case. It also seems to me that when you do modulation theory, you want to modulate 2 wave trains that are wave trains that keep on seeing each other. It seems a little bit less interesting to study the NLS approximation when you have a wave packet which goes away and decays to 0 and eventually behaves very linearly. What you really want to do is a sustained interaction of a wave train. And so this is, okay, 1 upon time, 1 upon epsilon cubed, but it's not exponentially long and it's not forever. But I think that's because you have to be we're in a situation where there's sustained interaction. So there are results, and now I didn't put them on my slides because I wasn't planning to talk about that, but let me make sure everyone gets good credit. There's Sijir Wu in 3 dimensions, that small data solutions can last for all time. There's Masmoudi and Chattah, Germain, Masmoudi, and Chattah, who have a paper who says that in 3 dimensions, solutions last for all time. There's a paper by Tots and Wu, who study the NLS limit of solutions in 2D, at least for a long time, because they have theorem that solutions exist for a long time. There's contributions by, oh boy, I'm live on the air and I'm having to pull these all out of memory, so I'm going to get funny emails tomorrow. But let's see, there's contributions of John Hunter, Daniel Tataru, and Ephraim, and maybe somebody else. I'm sorry, I forgot your name. That's to the live audience out there. Which again, redo this, I think it's the two-dimensional case because they use conformal mapping variables. And there is also a paper by Thomas Alazar and Delors, which in 2D, it's a very complicated paper, but in 2D they get global existence. This is all in the setting of waves spreading out and dispersing. So that's a different story than the one where you are forcing it to have sustained self-interactions. You will never get decay of amplitude. It just it goes on and on. So that's the setting I'm in. Satisfy the?
More than enough.
Yes, please.
I have simple question. So, how to reconcile this beautiful picture with the reality of exact numerical simulations? So, that is kind of exact. So, I take a periodic domain, and I take initial conditions, some perturbation, and so after, if say, let's be more specific. So I start with a slightly perturbed uniform wave, and after a while, so the wave breaks, so that it develops singularity, which is kind of eliminated in your treatment. You say you can guarantee global existence for infinite time, but what happens?
I just cited all the people who can do the guaranteeing. I can't guarantee. So are your numerics periodic or?
Yes, yes.
Okay, well these theorems are all for infinite domain. So then what you have to compare is this finite length of existence time, that 1 upon epsilon to a power. That would be the thing to compare. And I also have to say the disclaimer that is, a theorem is a lower bound on existence time. If you produce a solution which makes a singularity, which I have not done, that's going to be quite hard for this equation. Lovely waves up there still. It feels good, actually. It's warm here. Then I can get an upper bound, but the existence theorem is a lower bound. So what we have to compare, you and I, is how long your solutions last with the measure of epsilon, and how long I'm guaranteeing them to last. So that's the story. So it makes a big difference between a compact domain and a non-compact domain, or a domain where you can send things to infinity and you get guaranteed amplitude decay versus when not. That's probably the difference.
I have periodic boundary conditions.
So you're closer to me.
Yeah.
Closer to me, where all that stuff I said verbally is the stuff I didn't put on my slides because I was talking about the periodic case. Shall I go on?
So to clarify if I understood this, in the periodic case, if you have initial data of order epsilon, then you can expect an existence times of order 1 over epsilon cubed.
Expect is the key word because it's not a theorem yet.
So it's not inconsistent with what he just described.
No. Well, he has to compare his epsilon to my epsilon, etc. Yeah, but it's not at all. It's reasonable. But I would expect him to have to wait for a certain amount of time before a singularity.
So what I would like to say that whatever the definition of epsilon, the discrepancy would be in the next order in epsilon. Whatever, you understand that. So it's,
Or if your singularity occurred in a shorter time.
Then we would have to have an argument.
Yeah. Okay.
Yeah. Okay, so I'd like to prove 2 theorems for you, at least sketch the proof. So what I need is a transformation to eliminate nonlinear terms in my Hamiltonian? Well, so one of the key things is you need a source of canonical transformations. And okay, I think that there are three classical sources. One source is you just make it up out of your head, or you take things that you know are canonical, then you use them. And some simple things are of course available, and you use what you can. But to be more systematic, you have to design a canonical transformation. To be more systematic, there are two methods. One is the method of generating functions, which I will not talk about in this talk. The second method is to use the fact that the flow of a Hamiltonian system is itself a canonical transformation. What is the flow? It's the solution map. You take a data point and you solve for time t. Let's make t equal 1 for agreement. But then you take all data points and you solve for time t, the same t equals 1, and that moves all points. And that's a transformation which for Hamiltonians, if you're solving a Hamiltonian system, that's guaranteed to be canonical. So let's adopt that strategy. So my flow is not t. It's a parameter flow, which I'm going to start at 0 and deform until I get to 1, and then I stop. That's my transformation. So I'm going to what I'm going to do is design a k such that the flow of the Hamiltonian system with that Hamiltonian k is going to be the right transformation. So that tells me I have to find k. Now, of course, this is Birkhoff's beautiful idea. Everything is nonlinear. The flow is nonlinear. My system is nonlinear. Solving the equation is nonlinear. Everything I can think of is nonlinear except for one piece of this, and that's the equation for k. Turns out to be a linear equation, which I see I haven't written on the blackboard. So finally, I get to use the chalk, which is what's the equation for k? Well, whoops, what did I do?
Just write the equation and put the chalkboard back down.
Oh, it might come back. It is h2 modulo sines k3 Poisson bracket. I have to eliminate h3. If there are any resonant terms, I take them out by averaging. And this will leave in the Hamiltonian. If I follow this and I use the flow, it will leave in this transformation, take away everything in h3 except its average. Let's see. Wow, that's a nice button on the technology. Somebody's been here before. Okay, so let's just study K3 in this case of 2 dimensions and h is equal to infinity. Well, it turns out to be remarkably simple. To tell you the truth, I did it the hard way. I calculated about 10 pages, and then it came out to be simple, but I'm going to do it backwards, which makes it a lot easier. So K3 turns out to be C, the D times the Hilbert transform of C, and then the Hilbert transform of eta squared. Well, why don't I write it in so many Hilbert transforms, why don't I write it in terms of the Hilbert transform itself? So if I take eta C and I Hilbert transform them both, then it's eta squared d by dx of C, eta tilde squared d by dx of C tilde. Oh, by the way, this is a canonical transformation. It's one of the first type. You just pull it out of your head. Okay? Then what am I supposed to do? I have to flow this system. And the solution map will give me the canonical transformations. Well, it's so simple. Let's do the eta flow first. D by ds, s is time, d by ds of eta tilde is equal to minus eta tilde Burgers. That was amazing. Isn't that funny? So I've solved Burgers' equation. That's the gradient with respect to xi tilde, right? And then the xi is Burgers essentially linearized around the curve eta that you find. And it's Burgers' flow and its linearization. And this is somehow Hunter and Ifram also found this, at least on the eta level, and used that, although they don't do it in the Hamiltonian framework.
Solutions of the first equation blow up in finite time?
But you have the choice, they do. Every solution except the constant blows up. But you have the choice of a neighborhood. And you have to flow till time 1. Remember, we chose time 1? The neighborhood's small enough, they'll stay smooth up to time 1. That'll dictate how big your neighborhood is. Bigger, it gets worse. And it's on the Hilbert transform side, a little bit unexpected.
So when you say burgers, you mean inviscid burgers?
Inviscid burgers. This burgers. Take this and cut it out.
Is there a
Inviscid burgers.
equality sign too much, or?
Sorry?
is there
Oh,
perhaps a-
this is equal to this, and this you calculate as equal to this. Oh, and no, this is equal to that. Everything's right. A lot of equality signs, but everything on that line is equal. Everything on the next line is equal. The first two are an equation, and the second two are comes from here. Just wanted to show you. Okay. We have to check that that's true. So let's do Poisson brackets in our head. I did it down here. But, but H3 average is 0. I explained, Peter explained that to us. There are no three-way resonances. So let's check that if I take the Poisson bracket of H2 and K3, I get the right answer. So Poisson bracket is eta d sine eta squared, some things. And if I adjust this a little bit, I find a total derivative, so it's 0, minus sine d eta dxc mod dxc. Now, there's something about Hardy space functions and the Hilbert transform that looks a little bit like the Leibniz rule. That is, when you differentiate a product, you get the sum of things. And so that identity, in terms of the Hilbert transform, says if I have f plus ig as a Hardy space function, that is, g is the Hilbert transform of f, then the difference of the squares is the Hilbert transform of the product. It's funny, sort of, Leibniz rule. And if I just plug this in, where f is d by dxc, and g is I sine d by dxc, I get a difference of squares, which turns out to be, funnily enough, the third order term of the Hamiltonian. Okay, that's interesting fact. Proof of theorem 2, it's not so straightforward. But you do the following thing, figure out the resonance. This is the first time I've written down surface tension. Here's this dispersion relation. You can find resonant triplets. They lie in a compact set in K space. If sigma is really small, it might be a large compact set, but compact nonetheless. There can be resonances, but aside from them, you can remove all non-resonant triads. That means you have to solve this equation. So it's again linear for K3. You find out what K3 is. It's a 10-page or a little bit more calculation. You find its Hamiltonian vector field. You study it, and it turns out to be Lipschitz on that Sobolev space that I complained. But now you need R bigger than 1. Okay, extra half. I'm ready to give that to you. And the Lipschitz estimate means when you do the Picard iteration, that is method of successive approximations, it's a uniform bound. And so therefore, everything you converge to something which is analytic with respect to its parameters, because the parameters enter analytically, in particular the initial data. And so it turns out to be an analytic canonical transformation. So that's enough proof for theorem 2. Now the final thing, which is a critique. Well, it's actually work in progress because we haven't solved the basic problem, which is we would like to show a long time existence theorem. So my excuse for not having done so is that in every coordinate system, there's some sort of trick which mathematical analysts use in order to show that solutions to the Euler's equation with free surface exist. In 2 dimensions, that trick turns out to work very well in Lagrangian coordinates. And I'm slipping my mind the name of the person who showed that, but it's a colleague of Pavel Plotnikov. Please tell me his name.
Yes. What?
The existence. Nalimov, thank you. Nalimov discovered this trick, but it works in Lagrangian variables in 2 dimensions. Oh, also similar in 3 dimensions. In Euler equations, every proof I know more or less circles around the fact that Alinak introduced good variables. Because otherwise there are terms in derivatives which may result in instability. You don't know, but you need, the variables are a detail that you need to get right. And it's not so clear after the normal forms transformation what the tail is when I'm expecting it to be something, which needs to be discovered. Here's another thing I should critique. The case I left out, finite depth, even constant finite depth. It's a funny thing, there's an extra cancellation when the depth is infinite, which was not there for finite depth. So it leaves me a little bit stymied. No surface tension turns out to be a little bit smoothing in this business. No surface tension, but finite depth leaves me with a question mark at the moment. So anybody have information? I'm happy to talk about it. What should happen if you have variable bathymetry? Well, variable anything, I guess anything could happen. But how about we just stick to periodic? Well, then there should be a sequence of Bragg functions. There should be a sort of a block theory, sequence of Bragg frequency functions, and the triples and things should be the Bragg frequencies. So that'd be an interesting sideline to develop, but could be rather there's a little bit of technology involved. And then I have to note that there's a natural energy for the Hamiltonian, which involves R derivatives of eta. So without surface tension, it involves R derivatives of eta, because that's the potential energy, and R plus 1/2 derivatives of C, because that's the Dirichlet-Neumann operator. Yet my spaces are not quite the energy spaces. This is an energy space, and instead of the 1/2 being here, I put it over here. That's what was needed. I'm sorry. So it's a little bit funny. It doesn't quite sit in energy space. So it's also a question that I'm asking myself, but and don't have an answer to. So my next slide is the hardest one. Thank you very much.
Any questions?
Yes, please.
In your very opening remarks, you talked about what a normal form is. You talked about changing variables to change the nonlinearity, while retaining the flat skewed form of the Hamiltonian system. So the J is the J matrix is the multiplier. But the Hamiltonian systems can have non-linear skewed forms.
Sure.
So if you relax that condition, can't you get an easier way to eliminate and to improve your nonlinearities in the differential equation? The price you're paying is that you have a more complicated skewed form.
Right. So, well, let me preface that by saying a normal form, well, it depends on what you consider to be normal.
That's
And
exactly my
and
point.
yeah, and if you consider something more relaxed to be normal, that's fine. I think in the end, in Taylor expansion, you're going to the three-wave resonances are really there when they are. I mean, say in the surface. So we're not going to finesse them being there. They're going to still be there, but we might be able to do some other thing. I think in Taylor expansion, you're going to end up finding the same thing around 0. And in fact, the coefficients of the z's are known as the Birkhoff invariants. They're actually invariants under family of canonical transformations. But you're free to do anything, and that's what you consider to be normal.
But Sakharov and company did exactly what I was talking about in '96 when they made a change of variables that turned the Hamiltonian system into a system with linear and quadratic terms only.
Mm-hmm.
And complication was that the skew form was complicated.
Right.
But I mean, and sorry, there were two complications. One was it contained only linear and quadratic terms, but it was quasi-linear rather than the centimeter.
Right.
So I mean, I don't think this has been pursued.
I'm open-minded. It depends. It
And
depends.
the traveling wave problem is simply a quadratic equation.
Yeah. Okay. For example.
Walter?
Yes. Yes, please.
Thank you for your presentation. You just had a small remark on at the beginning of your talk. You talked about eta and psi being the canonical variables, right?
Well,
I mean,
I avoided the word the
Well, I mean,
because a
that's all right.
pair of canonical.
But there is another way of deriving it rather than spotting it. You start with the kinetic energy, with still U Q in it, so not
Yeah.
potential yet. And the potential energy, and you add Lin constraints, one for the incompressibility, so using pressure as a Lagrange multiplier, but then one where you add the continuity equation with phi as your velocity potential. If you work that through, you actually get loops and then subsequently Miles variational principle in a derived way. You end up with the same result, of course, but that's another way of doing it.
Very good. So contribution to the lecture. Thank you.
And then I have
That's
another.
written in Selinger paper of about 1970 something.
There you are.
And a very small question to enlighten me. You wrote down this operator in the beginning G of eta, right? Now, in the case when you still have a domain which is like, well, say 2D, your 2D, which is topologically equivalent to a rectangle, but it is overturning. Can you also
Of course.
define
Of course.
that? But then, because
Of course,
then
but you have to
there's no-
change. I gave it in particular variables, but I cannot no longer do that.
Yeah, you can't use eta.
I cannot do, and of course, there might be some argument why I gave those very Cartesian restricted coordinates in the first place.
But you can lift that.
Yeah, it's you can be open-minded. And in fact, it's a good idea to put it in Lagrangian,
Right.
because then the Hamiltonian is going to be actually quite clear as you go on.
Okay.
Yes.
May I ask you, Alazar and Delors
Yeah.
use some trick to killing some terms in equation in order to get critical decay at infinity and get global existence theory in 2D case. This trick was from our paper with Girard. There is some equation with Q-symmetric operator which kills something like this. It is simple things, of course, with respect to you, but maybe there is some relation between your researches and this Alazar and Delors.
Well, I find that paper a complicated paper, and I even find their methods a little bit screwy. I mean, I would have approached it in a different way. So they have their own philosophy, which often I agree with, but in this paper I found it confusing. But there's a difference because they work on the line and you work on the periodic interval. But
yes, they're working on real line.
Right.
But it is one-dimensional gains and scheduling is very, very slow.
right. Okay.
For this
So you probably know that paper better than me.
Okay.
Yes.
So you mentioned the Hadamard's formula and quoted some papers of Hadamard. So is there any modern exposition of this? I mean, can it be found in your paper or something?
The funny thing is, for a long period I thought it was forgotten, and I learned about it from Garabedian's book. So Garabedian has a very nice PDE book, and it has regular chapters till about 2/3 of the way through, and then it has these short supplementary chapters, and it's one of the short supplementary chapters. So there's a, if you permit me 30 seconds, there's an interesting history over this, because the variational formula of Hadamard, really it's the resolvent formula, but as you vary domains, resolvent think you vary the energy lambda, but here you're varying domains. But that's not the only elliptic system that for which it's interesting. It's also interesting for the Cauchy-Riemann equations, and there it's known as the Schiffer variational principle, I believe, and that's also in Garabedian's paper. And why were these Stanford guys interested in it? It's because it was related to oh damn, I'm forgetting the name. The conjecture on the sorry?
Birkhoff.
The Bieberbach conjecture, the optimal Schlicht mapping of a disk. And their strategy was to pick off coefficient after coefficient of the Taylor expansion of the optimal mapping, and they got the third and the fourth, I think, with this variational formula. And then it choked, and only later was fully solved by completely different methods. But it has a kind of interesting